Mercury is the closest planet to the Sun, but almost nobody talks about it. And that's genuinely strange, because Mercury is actually one of the most fascinating and mysterious places in our entire solar system. It's small, it's violent, and it contradicts almost every single assumption we have about how planets work. So before we get started here, if you're interested in space, in science, in the weird and mysterious corners of our solar system, please like this video and subscribe. It genuinely means the world when you do. Let me know in the comments where you're tuning in from and what time it is for you right now, at this moment. It's always genuinely fascinating to see who's watching these videos from all over the world. Mercury has been overlooked for centuries, overshadowed by the more dramatic planets, the ringed beauty of Saturn, the red mystery of Mars, the massive giants of Jupiter. But Mercury deserves your attention because it's different in ways that challenge what we think we understand about planetary science. When you look at Mercury through a telescope, it doesn't tell you much. It's small, it's bright from the sun's reflection, and it's hard to see clearly because it's always hiding near the sun from our vantage point on Earth. Astronomers have struggled to study it, and even now, after centuries of observation, we're still discovering things about Mercury that surprise us, that confuse us, and that don't fit neatly into our models. What makes Mercury so strange isn't just one thing. It's everything combined. The planet's location, its orbit, its rotation, its internal structure, its magnetic field, its surface features. All of these work together to create a world that seems almost designed to break our understanding of how planets should behave. Mercury is the smallest planet in our solar system, just slightly larger than Earth's moon. If Earth were the size of a nickel, Mercury would be about as big as a blueberry. Imagine that, an entire world the size of a blueberry, orbiting 36 million miles away from a massive star that dominates everything around it. From that distance, which is only 0.4 astronomical units from the Sun, sunlight takes just 3.2 minutes to travel from the Sun to Mercury's surface. Despite how close Mercury is to the Sun, it remains one of the least explored planets in our solar system. Spacecraft struggle to reach it, the environment is hostile beyond comprehension, and the few missions that have made it there have brought back data that raises more questions than it answers. Mercury's orbit is strange. It's not circular like you might expect. Instead, it's highly elliptical, egg-shaped, taking the planet as close as 29 million miles from the Sun and as far as 43 million kilometers away. This extreme variation is the highest orbital eccentricity of any planet in our solar system, a difference of 24 million kilometers, a swing of 53% in distance. The variation in distance creates variation in solar radiation, in gravitational forces, in the entire energetic environment Mercury experiences. The planet orbits the Sun once every 88 Earth days, moving faster than any other planet in the solar system, traveling at nearly 29 kilometers per second. But this isn't just impressive speed. It's the foundation of something far more complex. The elliptical orbit means that Mercury doesn't experience a uniform solar environment. Some parts of its orbit bring it much closer to the intense solar radiation and gravitational field of the Sun. Other parts take it slightly farther away, giving the planet a moment of relative relief. This variation has shaped Mercury's geology, its magnetic field, its entire existence. Scientists believe this unusual orbital configuration may have resulted from massive impacts early in the solar system's history. The young solar system was chaotic. Planets were forming, moving, colliding. Mercury's elliptical orbit might be the leftover signature of that chaos, a relic of impacts and gravitational interactions that have long since settled. The orbit is stable now, locked in place by physics, but it remembers its violent past. But speed and orbit alone don't explain what's happening with Mercury's rotation. And this is where things get weird. Mercury spins on its axis very slowly, completing one rotation every 59 Earth days. That's slower than its orbital period. But here's the thing. Mercury's rotation isn't random. It follows something called a 3-to-2 spin-orbit resonance, meaning the planet rotates exactly 3 times for every 2 times it orbits the Sun. This relationship was discovered by radar observations in 1965, and it's unique. No other planet in our solar system has this exact configuration. The resonance is maintained by gravitational interactions between Mercury's enormous iron core and the tidal forces exerted by the Sun. It's a stable configuration that has persisted for billions of years, locked in place by the physics of orbital mechanics. The consequences of this rotation are almost unimaginable. A solar day on Mercury, one complete day-night cycle, equals 176 Earth days. That's just over 2 years. Imagine standing on Mercury's surface and waiting for sunset. You'd wait months. And when sunset comes, something bizarre happens. In certain locations on Mercury, the sun doesn't simply set. It rises partway over the horizon, then reverses direction, setting again, and then rising once more in the same Mercurian day. This happens because approximately 4 Earth days before Mercury reaches its closest approach to the Sun, called perihelion, the planet's orbital velocity equals its rotational velocity. At that moment, the Sun appears to stop moving in the sky. Then, as Mercury continues toward perihelion and begins to move faster in its orbit than it rotates, the Sun appears to move backward, in retrograde motion. This is one of the most disorienting phenomena you could experience if you were standing on another world. Mercury's axis is tilted just 2 degrees with respect to its orbital plane. That's almost vertical, compared to Earth's 23.5-degree tilt. This minimal tilt means Mercury has no seasons. There's no variation in sunlight intensity across the year. The climate, extreme as it is, remains consistent. Thermal stress on the planet comes from the daily temperature swings, not seasonal cycles. And those temperature swings are catastrophic. Mercury's daytime surface temperatures reach 800 degrees Fahrenheit, 430 degrees Celsius. That's hot enough to melt lead. But without an atmosphere to retain heat, when night falls, temperatures plummet to minus 290 degrees Fahrenheit, minus 180 degrees Celsius. The temperature difference is approximately 1,100 degrees Fahrenheit, the most extreme temperature variation of any planet in our solar system. This constant cycling of expansion and contraction shapes the entire planet, creating stress fractures, releasing volatile materials from the subsurface, and driving geological processes that are still active today. Despite being closest to the Sun, Mercury is not the hottest planet in our solar system. That title belongs to Venus, the second planet. This seems backward, counterintuitive, but it's absolutely true. Venus has an atmosphere, a thick blanket of gases that traps heat through a runaway greenhouse effect. The average surface temperature on Venus is 864 degrees Fahrenheit, 462 degrees Celsius. That's higher than Mercury's maximum temperature. Mercury has no atmosphere. It lost its primordial atmosphere about 4.6 billion years ago, soon after the planet formed. The atmosphere dissipated under intense solar radiation, under the solar wind, and possibly under bombardment from massive impacts. Without an atmosphere to retain heat, Mercury loses warmth directly to space. The night side gets no help from global winds or atmospheric circulation. The heat simply escapes. This is a crucial lesson about planetary science. Proximity to the Sun alone does not determine temperature. The presence or absence of an atmosphere is what matters. A planet closer to the Sun, but without an atmosphere, can be cooler than a planet farther away with a dense atmosphere. Mercury teaches us that intuition can be misleading, that the universe follows rules that don't always match our expectations. Mercury's internal structure is unlike any other planet. It has a central core, a rocky mantle, and a solid crust, like the other terrestrial planets. But Mercury's core is enormous. The core has a radius of about 1,289 miles, 2,074 kilometers, accounting for about 85% of the planet's radius. For comparison, Earth's core is only about 17% of Earth's volume. Mercury's core occupies about 57% of its entire volume. This is an extraordinarily large iron-rich core, and it's what makes Mercury so dense despite its small size. Mercury is the second densest planet in our solar system, after Earth. But here's where it gets mysterious. Mercury's core is not fully solidified. Evidence suggests it's partially molten, at least in part. There's a liquid outer core surrounding a potentially solid inner core. This was unexpected. Scientists initially thought that a planet Mercury's size would have cooled and solidified completely over the 4.6 billion years since its formation. The heat from radioactive decay would have dissipated into space. The core should be dead, dormant, solid. But Mercury's core is still warm. It's still partly molten. Scientists believe this might be because of sulfur, or another light element in the core, that lowers the melting point of the iron. The exact composition of Mercury's core remains uncertain because we haven't been able to directly study it. We infer its properties from orbital measurements, from the planet's density, from magnetic field observations. Mercury's outer shell, the mantle and crust combined, is only about 250 miles thick, 400 kilometers. Imagine a planet so imbalanced, so weighted toward its core, that the thin rocky skin covering it is proportionally thinner than the skin of an apple. This thin outer layer contrasts dramatically with the enormous metallic ball beneath. And this structure has consequences for everything else about Mercury. The massive core creates a gravity field that held the planet's shape. The cooling core creates stress that fractures the thin crust. The molten portions of the core might be responsible for Mercury's magnetic field, one of the most puzzling aspects of the planet. Mercury is shrinking, not quickly, not visibly in a human lifetime, but measurably over geological time. Astronomers estimate that Mercury is about 9 miles smaller in diameter than it was 4 billion years ago. As the iron core cools, it solidifies, and as it solidifies, it contracts. This contraction is reducing the planet's volume. The shrinkage must have continued until comparatively recently in Mercury's geologic history, because some of the youngest impact craters on the planet show signs of being deformed by these contraction features. The fact that Mercury continues to shrink even today suggests that interior cooling and contraction processes are still actively shaping the surface. Some thrust faults and scarps appear to be less than 50 million years old, indicating ongoing geological activity. Mercury is not a dead world. It's slowly crushing itself from the inside out, and that process is far from finished. Mercury has no real atmosphere, just a thin exosphere made of atoms blasted off the surface by the solar wind and by meteorite impacts. The exosphere is composed mainly of oxygen, sodium, hydrogen, helium, and potassium. It's so tenuous that even the sharpest spacecraft cameras can't see it directly. Yet this exosphere plays a crucial role in how Mercury interacts with the solar wind, in how the planet loses material, in the ongoing evolution of the surface. Without an atmosphere, Mercury has no weather, no wind, no clouds. The sky is always black, even during the day. If you stood on Mercury's surface, you wouldn't see the blues and gradients of a sky. You'd see black above you and brilliant stars visible in that black, even while the sun burned in the horizon. There's no protection from solar radiation, no buffering, no escape from the harsh environment. This lack of atmosphere contributes to the extreme temperature variations, the intense solar wind effects, and the overall hostility of Mercury to anything we might consider life. But Mercury has something nobody expected to find there. Mercury has water ice. In 2012, NASA's Messenger spacecraft discovered water ice inside some of Mercury's craters. In 2017, it was confirmed that Mercury has much more ice scattered across its North Polar region than previously thought. This seems impossible. Mercury is the hottest planet by daytime temperature. How could there be ice? The answer lies in Mercury's geometry and its relationship with the Sun. Some impact crater floors near Mercury's poles are permanently shadowed, regions that never receive direct sunlight. In these permanent shadows, temperatures remain far too cold for ice to sublime, to evaporate directly from solid to gas. Temperatures in these regions stay below minus 170 degrees Celsius, minus 280 degrees Fahrenheit. Water ice can survive in these conditions indefinitely. The ice might have been delivered by comets and asteroids early in Mercury's history and preserved in these dark places. Or it might have been created through chemical processes, hydrogen from the solar wind interacting with surface materials to produce water molecules that accumulated over billions of years in these shadowed craters. The origin remains uncertain, but the existence of ice on Mercury is a reminder that planetary science constantly surprises us. Mercury has a magnetic field, which is remarkable because it shouldn't. Mercury is small. It rotates slowly over 59 days, and scientists once thought small planets would lose their magnetism over billions of years as their interiors cooled. But Mercury has a global magnetic field. It's weak compared to Earth's. It's only about 1.1% the strength of Earth's magnetic field. At Mercury's equator, the field strength is about 300 nanotesla. But it's there. It's real. It's apparently global. This was discovered by the Mariner 10 spacecraft in the 1970s. Mercury and Earth are the only rocky planets in our solar system with significant global magnetic fields. Venus and Mars lost their fields as their cores cooled. So why does Mercury still have one? Here's the mystery. Mercury should have a much stronger magnetic field. The planet is extraordinarily iron-rich. Its metallic core comprises about 2/3 of the planet's mass, roughly twice the ratio for Earth, Venus, or Mars. Given this composition, given how much iron is in Mercury's core, the planet should have a magnetic field about 30 times stronger than what we actually observe. The weakness of Mercury's field compared to what its composition suggests is one of the greatest puzzles in planetary magnetism. Scientists have proposed that the solar wind might be responsible. The solar wind deflects charged particles in Mercury's magnetosphere, the magnetic bubble surrounding the planet. This magnetosphere extends only about 5% as far as Earth's magnetosphere. It's small, it's compact, it's dynamic. The magnetic field from this magnetosphere might reach all the way to Mercury's core, limiting the strength of the field created by the planet's interior. The solar wind, constantly buffeting and distorting Mercury's magnetosphere, might be suppressing the magnetic field that Mercury's core would otherwise generate. This explanation remains unconfirmed, but it's the leading hypothesis. Mercury orbits in a unique regime, where the solar wind is still fresh from the sun, where the sun's magnetic field strength is rapidly waning with distance. Mercury's highly elliptical orbit means the planet passes through a wider range of distances from the sun than any other planet. This provides a natural laboratory for studying how the sun's influence on a planet varies with distance. The variation in distance is enormous in proportional terms. Mercury's magnetosphere extends only about 5% as far as Earth's magnetosphere. It's a small, compact bubble of magnetic protection in a hostile space environment. As Mercury moves from aphelion, its farthest point from the Sun, to perihelion, its closest approach, it experiences dramatic changes in solar, wind intensity, in solar radiation, in gravitational forces. The magnetosphere responds rapidly to these changes. The characteristic timescales for convection and wave transits through Mercury's magnetosphere are only 1 to 2 minutes, nearly 2 orders of magnitude shorter than at Earth. At Earth, it takes hours for changes in the solar wind to propagate through the magnetosphere. At Mercury, it takes minutes. Mercury's magnetosphere is constantly reshaping itself, responding to solar wind variations in real time, pulsing and changing almost moment to moment in response to conditions in the solar wind. Under normal conditions, Mercury's intrinsic magnetic field is strong enough to keep the solar wind from reaching the surface directly. Particles from the solar wind can only reach Mercury in the cusp regions, openings in the magnetosphere where field lines are open to space. But during coronal mass ejections, massive explosions on the Sun, the magnetopause gets pressed into Mercury's surface. The solar wind can interact freely with the planetary surface. This interaction happens multiple times per year, and its long-term effects on Mercury's surface and exosphere remain an active area of research. Mercury's surface is covered in craters, more craters than any other planet in our solar system. Unlike many other planets that undergo geological processes that erase or modify impact craters, Mercury's surface has remained largely unchanged for billions of years. Without an atmosphere to weather craters away, without plate tectonics to reshape the surface, without significant volcanic activity to bury old features, the craters accumulate. Over 440 craters have been formally named on Mercury, and they represent only a tiny fraction of the total craters on the planet's surface. The naming convention for Mercury's craters is distinctive. According to the International Astronomical Union's rules, all new craters on Mercury must be named after artists who were famous for more than 50 years and dead for at least 3 years before being named. This means Mercury's surface is dotted with craters named after famous writers, composers, artists, and musicians. Children's author Dr. Seuss has a crater. Dance pioneer Alvin Ailey has a crater. The Mercurian surface is a global monument to human creativity and culture. The heavily cratered nature of Mercury's surface provides scientists with a record of bombardment history extending back billions of years. Large impacts tell the story of early solar system chaos. Smaller impacts tell the story of ongoing delivery of materials from space. The greatest impact feature on Mercury is the Caloris Basin. Caloris Basin is a massive impact crater measuring about 1,550 kilometers in diameter, about 960 miles across. The basin is ringed by mile-high mountains, concentric rings of elevated terrain created by the impact. For scale, the state of Texas is 773 miles wide from east to west. The Caloris Basin is larger. The impact that created Caloris happened about 3.8 billion years ago. Scientists estimate the impactor was at least 60 to 100 kilometers long, 37 to 62 miles. Imagine an asteroid nearly the size of a mountain crashing into a small planet at tens of kilometers per second. The impact was so powerful that it caused massive lava eruptions. Material was ejected across the planet. But the most remarkable consequence is invisible. The impact created shock waves that traveled through Mercury's interior, propagated all the way around the planet, and converged on the opposite side of Mercury, on the point directly antipodal to the Caloris Basin. At that antipodal point, something remarkable happened. There's a region on Mercury known as the Weird Terrain, located at the precise opposite point on the planet from the Caloris Basin. It's actually called that, the Weird Terrain. The shock waves from the Caloris impact somehow created a zone of chaotic, jumbled topography on the far side of the planet. The surface there looks distinctly different from anywhere else on Mercury. Fractured, disturbed, as if the entire area experienced a violent upheaval. The hypothesis is that shock waves from the impact traveled through Mercury's interior and collided at the antipodal point, converging from all directions simultaneously. This convergence would create tremendous stress, would fracture the surface, would jumble the terrain into the chaotic landscape we observe today. The Weird Terrain serves as remarkable evidence of the power and planetary scale consequences of the Caloris impact. Scientists have studied this region extensively because it provides insights into planetary seismic effects and impact mechanics that apply to understanding impacts on other bodies throughout the solar system. Mercury's surface shows other distinctive features created by the planet's ongoing contraction. As the iron core cooled and solidified, the planet contracted. The surface deformed to accommodate this contraction, creating wrinkle ridges and fault scarps. Mercury has some of the largest fault scarps in our solar system. The largest scarps reach lengths of 1,000 kilometers, 620 miles, and heights of 3 kilometers, 1.9 miles. These are dramatic geological features on a small planet. They represent a form of planetary scale contraction quite different from the plate tectonics active on Earth. Mercury's scarps are associated with thrust faults where the surface has broken and older rocks have been pushed up and over younger rocks. Most activity along the major thrust systems probably ended about 3.6 to 3.7 billion years ago. But small-scale thrust fault scarps have been discovered that appear to be less than 50 million years old, indicating that compression of the interior and surface geological activity continue to the present. Mercury is still adjusting to its own contraction, still reshaping itself as the core cools. Mercury also shows evidence of past volcanic activity. Smooth plains cover widespread areas, resembling the lunar Maria, the dark volcanic plains on the Moon. These smooth plains fill depressions of various sizes and notably fill a wide ring surrounding the Caloris Basin. Despite not having dramatic volcanic features like shield volcanoes, the evidence for volcanic origin is compelling and well established. The composition of surface materials, analyzed by instruments on visiting spacecraft, is consistent with volcanic rocks. Features resembling broad, gently sloping shield volcanoes have been spotted on the surface. The Mercurian smooth plains formed significantly later than the Caloris Basin, as evidenced by smaller crater densities on the plains than on the ejecta blanket around Caloris. The plains filled impact basins with lava flows, a process that occurred relatively late in Mercury's geological history, but certainly billions of years ago. The volcanic history of Mercury, while not as active as on some other rocky planets, was significant enough to reshape large regions of the surface, to fill depressions, and to potentially modify the climate conditions at the time. These volcanic plains provide scientists insights into the planet's geologic and thermal evolution, into the conditions in Mercury's interior during these volcanic episodes. Mercury's formation remains one of the great mysteries in planetary science. The standard model for planetary formations suggests that planets form from dust and gas in a protoplanetary disk, that materials condense and collide, that gravity pulls them together into larger and larger bodies. Mercury, being so close to the Sun, should have formed in a very hot environment. The early solar system was hot near the Sun, cold farther out. This temperature gradient should have influenced what materials could condense and form planets. Mercury should be more metal-rich than planets farther from the Sun, because volatile materials like water ice couldn't exist in the heat near the Sun's early radiation. The temperature at Mercury's distance from the young Sun would have been incredibly high, hundreds of degrees, hot enough that only metals and rocky materials with very high melting points could remain solid. Everything else would have evaporated, drifted away, remained gaseous. And indeed, Mercury is extremely metal-rich, but perhaps too much so. The planet's iron core is disproportionately large even for the inner solar system. This is where the puzzle deepens. Mercury's composition doesn't quite match what we'd predict based on its distance from the Sun and the distribution of materials in the early solar system. The discrepancy is dramatic. Scientists have proposed various explanations, each with different implications for understanding how the solar system formed and evolved. One hypothesis suggests that Mercury formed farther from the Sun, perhaps at the location where Venus now orbits, or somewhere between Venus and Mercury's current orbit. In the early solar system, before planetary orbits had stabilized, massive gravitational interactions between planets could have occurred. These interactions could have scattered Mercury inward, toward the Sun. An alternative hypothesis suggests that Mercury had a much thicker rocky mantle early in its history. Massive collisions with other planetary bodies, particularly a giant impact similar to the one that created Earth's moon, could have stripped away most of Mercury's mantle, leaving behind the disproportionately large core we observe today. This giant impact hypothesis explains Mercury's composition, but it's difficult to test and verify. Another possibility is that the solar nebula, the disk of dust and gas from which the planets formed, had a different composition structure than we currently understand. Perhaps at Mercury's distance from the early Sun, metals condensed preferentially over rocky materials, creating a naturally metal-rich body. Each hypothesis has supporters and detractors. The truth likely involves a combination of factors. Mercury's formation was probably complex, involving multiple processes, multiple collisions, multiple gravitational interactions that we're only beginning to understand. The formation of Mercury's massive core remains particularly mysterious. Iron is dense, much denser than rock. Heavy elements sink toward the center of a forming planet, a process called differentiation. But Mercury's core is so large, so disproportionate to the rocky mantle above, that the ratios seem extreme. Either Mercury has much more iron than we'd expect based on standard formation models, or Mercury lost much of its mantle through some catastrophic process. If Mercury had a giant impact that removed most of its mantle, what would that impact have been like? The impactor would have to be substantial, perhaps the size of the Moon, or larger relative to Mercury's mass. The collision would have been cataclysmic, generating enough heat to vaporize rock, to eject material into space, to fundamentally reshape the entire planet. Such an event would leave scars in Mercury's geology and orbital characteristics that we might still be able to detect. But Mercury's geology is complex and ancient. Differentiating between features created by such an impact and features created by other processes is challenging. Scientists continue to analyze data from spacecraft missions, to refine models, to test hypotheses. The truth is that Mercury's formation story hasn't been fully written yet. We have pieces of the puzzle, but we don't have the complete picture. The question of how Mercury acquired its massive iron core connects directly to another of the planet's great mysteries. The core is not only large, but apparently partially molten. How can the core still be molten after 4.6 billion years? The decay of radioactive elements in the core generates heat. Potassium-40, uranium-238, thorium-232, and other radioactive isotopes continuously release energy as they decay. This radiogenic heating has been sufficient to keep Earth's core partially molten for billions of years. This heat generation is literally internal combustion, nuclear decay happening silently in the darkness beneath the crust, atoms breaking down and releasing energy that keeps everything above hot and dynamic. But Mercury is smaller than Earth, so it should cool faster. A smaller body has a higher surface area to volume ratio, meaning more heat can escape from the surface relative to the volume of material generating heat. Think of it like a smaller pot of water cooling faster than a larger pot of water. The ratio of surface area to volume works against Mercury. More proportional cooling should have happened. By this logic, Mercury should have cooled completely, its core solidifying, its internal dynamo shutting down. But it hasn't. After 4.6 billion years, Mercury still has a molten core. The presence of a partially molten core suggests either that Mercury has more radioactive elements than expected, which seems unlikely given what we know about its composition, or that something is preventing heat loss more efficiently than we'd predict. The composition of the core, particularly whether sulfur or other light elements are present, affects the melting point of iron. A core rich in sulfur might remain molten at temperatures where pure iron would solidify. The exact composition of Mercury's core remains unknown. We haven't sent a probe to drill into the planet to measure the core directly. We infer its properties from the planet's overall density, from magnetic field measurements, from seismic data if we ever gather it. The partially molten core has consequences. It might be responsible for Mercury's weak but persistent magnetic field. A liquid outer core, moving and convecting, could generate a magnetic field through dynamo processes, the same mechanism that generates Earth's magnetic field. But if that's the case, Mercury's field should be stronger than it is, unless the solar wind is suppressing it, as current models suggest. The molten core also suggests that Mercury has more internal energy than we'd expect. That energy drives ongoing geological processes. It created the conditions for past volcanism. It continues to drive the contraction and fracturing we observe on the surface. Mercury may appear to be a dead, geologically inactive world, but its interior tells a different story. It's slowly changing, slowly cooling, slowly reshaping itself. The time frame is geological, billions of years, but the process is ongoing. Mercury is not frozen in time. It's a dynamic system, albeit a slow one, where deep internal processes continue to influence the surface world above. The iron heart of Mercury is a problem in the sense that it doesn't fit neatly into our understanding. It's an anomaly that forces us to reconsider our models of planetary formation. It's a challenge that drives researchers to develop new hypotheses, to gather more data, to refine our understanding of how planets form and evolve. Every measurement of Mercury, every observation, every analysis of data returned by spacecraft like Messenger adds another piece to the puzzle. But the full picture remains incomplete. Mercury's core, its composition, its formation, its ongoing evolution, these remain among the great unsolved questions in planetary science. The small planet closest to the Sun holds secrets that, when finally understood, will revolutionize our comprehension of how planetary systems develop and change. The volcanic history of Mercury shaped its geology in ways that persist today. But understanding why that volcanism occurred, understanding why certain features formed where they did, requires stepping back and looking at the bigger picture. Mercury's orbit doesn't just determine where the planet is at any given moment. It determines everything. The orbital mechanics cascade down through every system on the planet, from the interior to the surface to the thin exosphere above. They determine how much solar radiation hits the surface, They determine the gravitational stresses pulling on Mercury's body. They determine the very character of time itself on this small world. Mercury's orbit is egg-shaped, elliptical in the extreme. The planet comes as close as 29 million miles to the Sun, then swings out to 43 million miles away. That's a difference of 14 million miles, a swing of 48% in distance. For context, Earth's orbit is nearly circular. The variation in Earth's distance from the Sun from perihelion to aphelion is only about 3%. Mercury's variation is extreme by planetary standards and creates consequences that ripple through everything about how Mercury works. At perihelion, when Mercury is closest to the Sun, the solar radiation intensity increases dramatically. The Sun appears larger in the sky. The gravitational pull is stronger. The entire planet experiences an assault of energy and gravitational force that's almost unimaginable. Then Mercury swings outward, and the intensity decreases proportionally. The Sun appears smaller. The radiation lets up. The gravitational stranglehold loosens. This 48% variation in distance means that solar radiation intensity varies by a factor of roughly 2.3 from perihelion to aphelion. It's not a minor difference, it's transformative. The eccentricity of Mercury's orbit is the highest of any planet in the solar system. Only a few asteroids have more eccentric orbits. This extreme ellipticity is thought to be a relic of the early solar system's chaos. When planets were forming, gravitational interactions and massive collisions were reshaping planetary orbits constantly. Mercury might have formed closer to the Sun or farther from it. A giant collision or gravitational interactions with other planets could have pulled Mercury into this highly elliptical path. Once established, the orbit became stable. The laws of physics locked Mercury into this egg-shaped path, and despite billions of years, Mercury remains in this eccentric orbit. The eccentricity has consequences for Mercury's geology. The changing gravitational stress from the Sun creates tidal forces that flexed and stretched Mercury's body over time. This flexing generated heat in the interior. This heat drove volcanism early in Mercury's history. This heat kept the core warm enough to remain partially molten. The tidal stress also shaped Mercury's magnetic field interactions. The changing gravitational pull affects the rotation and orientation of the planet. It affects how the planet orbits and how the planet spins. Everything connects to that elliptical path. The orbit isn't incidental to Mercury's character, it's fundamental. It's the explanation for why Mercury is the way it is. The tidal heating from the elliptical orbit is particularly intense at perihelion. The gravitational forces are strongest. The internal stress is greatest. Over billions of years, this stress has accumulated. It has cracked rock. It has created pathways for magma to rise. It has modified the chemical composition of the interior as materials were broken down and recombined under pressure and temperature. The tidal heating varies throughout Mercury's orbit. At aphelion, when Mercury is farthest from the Sun, the heating is minimal. At perihelion, it's intense. This variation means that different parts of Mercury experience different thermal histories. Certain regions, particularly those on the subsolar point that faces the Sun at perihelion, experience repeated intense heating. Over time, these regions accumulate more thermal damage, more cracking, more chemical alteration. This creates heterogeneity in the crust and upper mantle. It creates regions of weakness where future volcanism might be more likely. The elliptical orbit, through its effect on tidal heating, has literally written Mercury's geology across the planet's surface. This extreme orbit comes with another consequence that took scientists by surprise. Mercury orbits the Sun extremely quickly. Its orbital period is only 88 Earth days. No other planet circles the Sun faster. Mercury is moving at nearly 47 kilometers per second, nearly 30 miles per second, hurtling through space in its eccentric path. This speed is remarkable when you consider the distances involved. Mercury covers the distance from Earth to the Sun in terms of orbital mechanics in less than 3 months. It makes more than 4 complete orbits in the time it takes Earth to make one. The speed, combined with the elliptical path, creates a dynamic, constantly changing environment for Mercury. The planet is never stable in its position relative to the Sun. It's always moving, always changing. Its distance, always in flux. This constant motion is part of what makes Mercury so difficult to study from Earth. The planet never sits still in the sky. It's always moving relative to the Sun, always hiding in the Sun's glare, always presenting different aspects to telescopic observation. Astronomers learned centuries ago that Mercury was difficult to observe, that it required patience and specific timing to catch glimpses of it. Now we know that's because Mercury is fundamentally different from the other inner planets. It's not content to sit in a stable orbit. It takes the most eccentric path it can manage and races along it at maximum speed. The energy from this orbital configuration is substantial. The gravitational potential energy stored in Mercury's elliptical orbit is enormous. This energy, converted into heat through tidal friction, has influenced Mercury's internal evolution. Early in Mercury's history, when the planet's interior was hotter and more ductile, the tidal heating was more effective. It melted rock. It drove convection in the mantle. It created the conditions for volcanic activity across the surface. Over billions of years, as the planet cooled, the effectiveness of tidal heating decreased. The interior solidified. The volcanism waned, but the effect persisted. The orbital configuration that created Mercury's present ellipticity also created the heat and stress that shaped everything about Mercury's geology. The eccentric orbit is not a curiosity. It's the foundation of everything that makes Mercury what it is. But the orbit alone doesn't explain Mercury's strange behavior. There's something else happening, something that seems almost designed, something that locks Mercury into a relationship with itself and with the Sun that is unique in the solar system. This is the resonance, the 3:2 spin-orbit resonance, and it's one of the most peculiar things about Mercury. Mercury rotates on its axis once every 59 Earth days. But here's the thing, Mercury orbits the Sun once every 88 Earth days. So the rotation period is about 2/3 of the orbital period. That's no accident. That's a lock. That's a resonance. Mercury rotates exactly 3 times for every 2 times it orbits the Sun. This relationship, called the 3:2 spin-orbit resonance, means that Mercury has been synchronized with itself in a way that seems almost impossible to achieve by chance. Radar observations in 1965 proved this relationship definitively. Before that, astronomers had no way of knowing exactly how fast Mercury rotated because the planet is so difficult to observe. But radar bounced off the surface, revealed the rotation. And the rotation period revealed a perfect relationship with the orbital period. 3 rotations per 2 orbits. Always, every time, with metronomic precision. Oh, the mechanism that maintains this resonance is gravitational. Mercury's elliptical orbit creates tidal forces. These tidal forces are strongest at perihelion, when the Sun is pulling on Mercury hardest. At perihelion, the Sun's gravity pulls on Mercury's far side more strongly than it pulls on the near side. This differential pull, this tidal force, creates a torque on Mercury's body. The torque tries to align Mercury in a specific way relative to the Sun. The eccentricity of Mercury's orbit means that this tidal torque is particularly strong and effective. The tidal force at perihelion essentially locks Mercury's rotation into step with its orbit. The mechanism is so effective that Mercury's rotation can't drift away from the 3-2 resonance. If Mercury started to rotate faster, the tidal forces would slow it down. If it started to rotate slower, the tidal forces would speed it up. The resonance is stable. It's maintained by the very forces that created it. This lock between rotation and orbit is unique among planets. No other planet in the solar system has such a precise relationship between its spin and its orbit. Why does Mercury have this resonance while other planets don't? The answer has to do with the strength of the tidal forces, the eccentricity of the orbit, and the properties of Mercury's body. Mercury has an enormous iron core relative to its overall size. The core creates a strong gravitational effect. The eccentricity is extreme. The tidal forces are strong. These factors combine to lock Mercury into the 3-2 resonance. Once locked in, the resonance is stable and self-perpetuating. Mercury can't escape it. The lock has persisted for billions of years and will continue as long as Mercury orbits the Sun. The 3-2 resonance creates consequences that reshape Mercury's experience of time and light. A solar day on Mercury, one complete day-night cycle, equals 176 Earth days. That's just over 2 Earth years. Imagine standing on Mercury's surface and waiting for sunset. You're waiting for months. When it finally comes, the Sun doesn't simply disappear below the horizon. In certain locations on Mercury, the retrograde motion of the Sun becomes visible. The Sun rises part way over the horizon, then stops. It reverses direction. It sets again, then it rises once more in the same Mercurian day. This bizarre dance of the Sun happens because of the 3-2 resonance. At certain points in Mercury's orbit, the planet's rotational motion and its orbital motion align in such a way that the apparent motion of the Sun reverses. The planet rotates faster than it's moving forward in its orbit, so the Sun appears to slide backward across the sky. This happens approximately 4 Earth days before perihelion, when Mercury's orbital velocity equals its rotational velocity. At that moment, the Sun appears to stop in the sky. Closer to perihelion, Mercury's orbital velocity exceeds its rotational velocity, and the Sun appears to move backward. This retrograde motion is perhaps the most disorienting phenomenon you could experience if you were standing on Mercury's surface. The basic mechanics of the sky, the rising and setting of the Sun, which seem fundamental and unchangeable from Earth's experience, don't apply on Mercury. The Sun misbehaves. It doesn't follow the simple rules we're accustomed to. This is what the 3-2 resonance creates. A world where the fundamental rhythms of day and night are broken and strange. The resonance also means that Mercury has synchronous heating. Certain regions on Mercury receive intense solar radiation at perihelion repeatedly. Because Mercury's orbit brings it back to the same position every 88 days, and because the rotation is locked to the orbit, certain parts of Mercury experience perihelion heating over and over. The same side of the planet faces the Sun during its closest approach repeatedly. This synchronous heating over billions of years has created thermal stress in the crust and influenced the geological evolution of specific regions. The synchronous heating means that Mercury's subsolar point, the location that faces the Sun most directly at perihelion, has been repeatedly baked by intense solar radiation for billions of years. This region experiences a unique thermal history that no other part of the planet shares. The constant repeated heating in the same location has created deep thermal scars. The rock has been fractured repeatedly. Volatile materials have been driven off. The surface composition has been altered. Scientists studying this region find evidence of intense thermal modification that extends deeper into the crust than anywhere else on Mercury. The poles tell a different story. The north and south poles of Mercury, due to Mercury's minimal axial tilt, never face the sun directly. They're locked in perpetual twilight. The temperatures at the poles remain relatively stable compared to the equator, and in shadowed craters at the poles, temperatures never rise above the threshold where water ice can sublimate. This is why Mercury has ice at the poles despite being the closest planet to the Sun. The 3:2 resonance, in conjunction with Mercury's axial tilt, creates a planet where certain regions experience extreme heating and other regions remain perpetually cold. The resonance has shaped Mercury's entire character. The synchronous relationship between rotation and orbit means that if you could somehow stand on Mercury and watch the Sun for a Mercurian day, you would see a pattern that never changes. Each Mercurian day unfolds almost identically to the last. The Sun rises, sets, and rises again, always in the same locations in the sky, always at the same apparent speeds. This regularity, while strange compared to Earth, is comforting in its way. It means that Mercury's relationship with the Sun is utterly predictable. There are no surprises. There are no storms or variations that would disrupt the pattern. The 3:2 resonance locks Mercury into an eternal rhythm with the Sun. Mercury's temperature extremes are unparalleled in the solar system. During the day, surface temperatures reach 800 degrees Fahrenheit, 430 degrees Celsius. During the night, they plummet to -290 degrees Fahrenheit, -180 degrees Celsius. The temperature difference is approximately 1,100 degrees Fahrenheit. No other planet experiences such a dramatic swing. This occurs because Mercury has essentially no atmosphere to buffer and distribute heat. Earth's atmosphere keeps heat from escaping too rapidly during the night. The air circulates heat around the planet. The water in the oceans absorbs heat during the day and releases it at night, moderating temperature swings. Venus has an atmosphere so thick it traps heat to a catastrophic degree. Mercury has none of these moderating factors. Mercury's daytime temperatures are hot enough to melt lead. At those temperatures, certain metals turn from solid to liquid. Rock itself softens. The surface of Mercury is being constantly thermally stressed, expanded and contracted, fractured and reformed. At night, the same surface contracts violently. Water, if it could exist on the surface, would be frozen solid. The extreme cold would turn gases into liquids. The temperature differential of 1,100 degrees means that materials on Mercury experience conditions that would destroy most things we're familiar with. The absence of atmosphere that causes these temperature extremes also means there's no weather, no wind, no clouds, no storms, no protection from radiation. The sky on Mercury is always black, even in the daytime. If you stood on Mercury during the day, you would see the sun, brilliantly bright, in a black sky. Stars would be visible at noon. The horizon would glow with heat radiation. But above your head would be black, the vacuum of space. The radiation falling on Mercury is unfiltered. There's no ozone layer to block ultraviolet. There's no atmospheric molecules to scatter and moderate the solar wind. The surface receives the full assault of the sun's radiation in all its forms. This radiation, over billions of years, has affected the surface composition. It's broken down minerals, it's created reactive compounds, it's contributed to the loss of volatile elements. The atmosphere Mercury had at formation, if it had one, was stripped away by this relentless radiation over billions of years. What remains is an exosphere, the thinnest possible shell of gas, composed of atoms knocked off the surface by the solar wind. and by meteorite impacts. The exosphere can't be seen. The atoms are too sparse. But it's there, a ghostly reminder that Mercury once had more atmosphere, or could have had more, and lost it to the hostile environment near the Sun. The temperature extremes have shaped Mercury's surface features. The constant expansion and contraction creates stress fractures. Materials that expand at different rates crack and break. The ancient lava flows that covered Mercury's surface have contracted and warped. The impact craters have been modified by thermal stress. The entire surface is a record of thermal violence extending back billions of years. Fresh-appearing impact craters show thermal modification, suggesting that the thermal stresses are ongoing and recent. Mercury is still being thermally modified. The planet is still in dialogue with the Sun, still being shaped by the extreme temperature variations that define its existence. Consider the physical demands placed on Mercury's surface by these temperature swings. During the day, the surface is exposed to nearly 430 degrees Celsius. The rock expands. Everything expands, and rocks are brittle with definite stress limits. When the entire surface expands by a measurable amount, that expansion has to go somewhere. It creates pressure and stress. If one layer of rock expands more than the layer beneath it, the upper layer can break. If rocks expand at different rates, they can separate. The surface cracks. These cracks aren't subtle. They're visible features that become the faults we see on Mercury's surface. Then night comes. The surface plunges to minus 180 degrees Celsius, and the rock contracts. Everything tries to get smaller. The cracks that formed during heating close, but not perfectly. The rock has been altered, and stress has been recorded in the crystal structure. This cycle happens once every Mercurian day, once every 176 Earth days, for billions of years. The accumulated damage is immense. The surface of Mercury is being shattered in slow motion by thermal cycling. Yet craters still have defined rims and central peaks, a testament to how strong rock is, even under terrible thermal stress. The thermal cycling has sculpted Mercury's geology as much as impacts have. It's a process with no equal on any other planet in our solar system. Mercury's surface is the most heavily cratered in the entire solar system. More craters cover Mercury than cover the Moon, than cover Mars, than cover any other body we've explored. Over 440 craters have been formally named on Mercury, and that's just a fraction of the total. The surface is scarred. It's pitted. It's been bombed by asteroids and comets for billions of years. Unlike Earth, where tectonic activity and weather erase craters, unlike other planets where geological processes modify the surface, Mercury preserves its scars. The craters accumulate. They overlap. They tell the story of billions of years of bombardment. Reading the surface of Mercury is like reading a book written in impact scars. Large craters tell stories of massive collisions billions of years ago. Smaller craters tell stories of ongoing delivery of material from space. The crater distribution shows patterns. Some regions have more craters than others. These density variations tell us the ages of the surfaces. Older surfaces have more craters. Younger surfaces, like those surrounding the Caloris Basin, have fewer craters, because they're younger, having been reset by the Caloris impact. The craters on Mercury have distinctive characteristics. The impact craters on Mercury tend to be well preserved. They don't slump and collapse like some lunar craters do, because Mercury's gravity, though weak, is stronger than the Moon's. The crater rims stay sharp. The central peaks stand clear. Ejecta blankets extend far from the impact site, and secondary craters from ejected material scattered across the surface. The craters tell stories of violent collisions. They show the angles of impact. They show the sizes of the impactors. They show what the surface was like at the moment of impact. The most famous crater naming convention for Mercury associates each crater with a famous deceased artist, musician, author, or cultural figure. The rules state that a crater must be named after someone who was famous for more than 50 years and dead for at least 3 years before the crater is officially named. This means Mercury's surface is decorated with craters named after creative people. Dr. Seuss has a crater. Beethoven has a crater. Tolstoy, Shakespeare, Michelangelo all have craters on Mercury. The planet's surface is a global monument to human creativity and culture, a celebration of the artists and thinkers who shaped human understanding and expression. The Caloris Basin dominates Mercury's geology. It's the largest known impact structure on Mercury, measuring about 1,550 kilometers in diameter, roughly 960 miles across. For scale, the entire state of Texas fits inside the Caloris Basin's diameter. The impact that created Caloris occurred about 3.8 billion years ago. The impactor was enormous, estimated at 60 to 100 kilometers across, 37 to 62 miles. Imagine a mountain the size of a small state crashing into Mercury at tens of kilometers per second. The impact was so powerful that it caused massive lava eruptions. The shock of the collision melted rock. Magma welled up from the interior and flooded across the surface. The impact ejected debris across the planet. Material was thrown thousands of kilometers away. The mountain-high rings surrounding the basin were raised by the impact. Concentric circles of elevated terrain reaching up to 2 kilometers high. The Caloris Basin is ringed by mile-high mountains created by the impact shock and rebound. The basin itself is filled with smooth lava plains, material that welled up from below in the aftermath of the impact. But the most remarkable consequence of the Caloris impact is invisible. The impact created shock waves. These waves traveled through Mercury's interior. They propagated around the entire planet. They converged on the point directly opposite the Caloris Basin. On the antipodal point, something extraordinary happened. A region known as the weird terrain erupted. The converging shock waves, arriving from all directions simultaneously, created tremendous stress. The surface fractured. The ground was jumbled and disturbed. A chaotic landscape emerged, distinctly different from anywhere else on Mercury. The weird terrain looks like the planet was subjected to a violent upheaval. The topography is fractured and disrupted. Ridges and valleys crisscross in patterns that seem random and chaotic. This is direct evidence of planetary-scale seismic effects. The impact on one side of the planet was so powerful that it shook the entire world. The waves that converged on the opposite side created visible damage. The weird terrain is a window into the scale and power of the Caloris impact. It's a reminder that an impact can affect an entire planet, not just the impact site itself. Consider the mechanism. The Caloris impact created a massive disturbance. The impactor was enormous, tens of kilometers across. The collision released energy equivalent to billions of nuclear weapons. The ground around the impact site was vaporized. Shock waves propagated outward at the speed of sound through rock. These waves traveled through Mercury's crust and mantle. They moved through the interior with barely diminishing intensity. They reached the far side of Mercury, the antipodal point, and approached it from all directions simultaneously. Imagine the convergence. Shock waves that left the Caloris Basin thousands of kilometers ago, traveling through the planet's interior, suddenly arrive at the opposite pole of the planet all at once. The energy that was dispersed through the entire planet converges at a single point. The stress becomes unimaginable. The rock can't accommodate it. It fails. It breaks. It shatters. The weird terrain is the result of that failure. It's a scar created by seismic waves that traveled a quarter of the way around the planet and converged with devastating effect. The feature demonstrates something profound about planetary impacts. An impact doesn't just affect the impact site, it affects the entire planet. The energy released ripples through the entire body. The effects are planetary in scale. Mercury's surface shows the scars of contraction. As the iron core cooled, it contracted. The solid crust above couldn't contract at the same rate. The surface had to adjust. It wrinkled. It broke. Thrust faults formed where older rocks were pushed up and over younger rocks. The largest scarps reach 1,000 kilometers long, 620 miles, and heights of 3 kilometers, nearly 2 miles. These are vast structures on a small planet. Mercury has some of the largest fault scarps in the entire solar system. The scarps represent a form of planetary contraction. Mercury is slowly crushing itself from the inside out. The core is cooling. The interior is contracting. The surface is deforming to accommodate this contraction. Most of the major thrust faults probably formed between 3.6 and 3.7 billion years ago. But recent discoveries have found small scarps that appear to be less than 50 million years old. Ours old. This means Mercury is still contracting. The process continues. The planet is still adjusting to the cooling of its interior. Millions of years from now, Mercury will be smaller than it is today. The contraction will continue slowly, inexorably, until the core has cooled and solidified completely. Then the contraction will cease. But that's billions of years in the future. Mercury's surface shows evidence of past volcanic activity. Smooth plains cover large areas of the surface. These plains resemble the lunar Maria, the dark volcanic plains on the moon. They fill depressions and basins. They cover areas surrounding the Caloris Basin. These smooth plains have crater densities lower than the surrounding terrain, indicating they're younger, formed more recently than the heavily cratered regions. The composition of the plains, analyzed by spacecraft instruments, is consistent with volcanic rocks. The plains are made of lava. They welled up from the interior and covered the surface. They formed relatively late in Mercury's geological history, perhaps 1 billion years or more after the planet formed, but still billions of years ago. The volcanic activity that created these plains was driven by heat from the interior. The tidal heating from the eccentric orbit, the radioactive decay of elements in the interior, both contributed heat that melted rock and drove volcanism to the surface. The volcanism has ceased. The interior has cooled too much to drive significant melting now. But the evidence remains. The smooth plains tell the story of a hotter, more geologically active Mercury. The Caloris Basin surroundings tell a story of this volcanism. A wide ring of smooth plains surrounds the basin. The impact melted rock and created pathways for magma to rise. After the impact, volcanic activity was intense in the Caloris region. Lava flooded the basin and surrounding areas. Over time, as the interior cooled, this volcanism waned. The plains we see today are the hardened lava that flowed across the surface billions of years ago. They're younger than the Caloris impact, younger than the surrounding cratered terrain, but still ancient by human standards. The hollows on Mercury are among the most mysterious features on any planet. They're bright patches scattered across Mercury's surface. They're young features, geologically speaking, with fresh edges and bright reflectances that suggest they're recent additions to the surface. Some hollows are tiny, just a few hundred meters across. Others are larger, stretching over kilometers. They're found in craters, on valley floors, on ridges and peaks. They're everywhere. The surfaces they're on are darker, older, heavily cratered. But the hollows stand out bright. They're clearly recent. They're clearly different. The mystery is what they are. What creates hollows? What makes them so bright? The leading hypothesis is that the hollows are exposed subsurface material. The surface of Mercury is covered in a layer of fine dust and regolith, material broken down by billions of years of impacts. This regolith is dark, weathered by the harsh space environment. Beneath it, the rock is fresher, less weathered, more reflective. The hollows might be places where the regolith has been removed, exposing the fresh rock beneath. But how does the regolith get removed? One possibility is solar wind sputtering. The solar wind, the stream of charged particles flowing from the sun, can knock atoms off the surface of exposed rock. Over time, this process removes atoms and exposes fresher material beneath. The sputtering is accelerated at the hollows because something about their chemistry or composition makes them more vulnerable to sputtering than the surrounding material. Another possibility is that the hollows are places where subsurface ice or volatile materials have sublimated away. If the subsurface contained water ice or other volatile materials, the heat from the sun or from impacts could cause these materials to vaporize. As they vaporize, they remove dust and regolith with them. The hollow is left behind, a depression where material has been removed. This volatile sublimation hypothesis is intriguing because it connects to Mercury's ice at the poles. If Mercury has subsurface volatiles that sublime away creating hollows, there's a mechanism for moving volatile material around the planet over billions of years. The distribution of hollows tells scientists something important about Mercury's subsurface composition. Hollows are not randomly distributed. They cluster in certain regions. They appear more frequently in areas associated with young volcanic activity, near fresh impact craters, and in specific geological units. This clustering suggests that the composition of the subsurface varies across Mercury. Some materials are more prone to losing regolith and creating hollows. Some regions are simply more active in terms of surface modification. The hollows might preferentially appear in mineral-rich areas. Mercury's surface shows evidence of compositional variation. Some regions are richer in certain minerals, elements, compounds. These compositional variations might make some areas more susceptible to the processes that create hollows. If solar wind sputtering is the primary mechanism, then areas with minerals that sputter more easily would have more hollows. If volatile sublimation is the primary mechanism, then areas with subsurface volatiles would have more hollows. The spatial distribution of hollows is actually a map of where these processes are active. The brightness of the hollows is remarkable. Some hollows are so bright they can be detected in radar observations from Earth. The reflectivity is extreme. This suggests that the material exposed in the hollows is not just fresh rock, but possibly material that's intrinsically bright. Some researchers have proposed that the hollows contain exposed crystal structures or mineral compositions that are particularly reflective. The bright material might be feldspar, a light-colored mineral abundant in planetary crusts. It might be fresh ice. It might be some other material with high reflectivity. The exact composition remains uncertain because we haven't sent a lander to analyze the hollows directly. The hollows are numerous enough that they must represent an ongoing process. They're not relics of the ancient past. They're features that form on relatively short timescales in geological terms. They're still forming. Mercury's surface is still being modified. The process creating the hollows is active. This is important because it means Mercury is not a static, unchanging world. It's a dynamic planet with ongoing surface modification. The hollows are evidence of that dynamism. They're proof that Mercury is being actively shaped by processes we're still working to understand. The hollows also tell us something about Mercury's subsurface. If the hollows are exposing subsurface material, then Mercury's subsurface has properties that differ from the surface. The subsurface is brighter, fresher, more reactive to the harsh space environment. This implies layering in the regolith. The top layer is heavily weathered. Beneath it, material is fresher. This layering has implications for how Mercury's surface has evolved. The weathering rate, the pace at which the surface is modified by the space environment, can be inferred from the depth of the regolith. The hollows provide windows into this process. The exact composition remains uncertain because we have not sent a lander to analyze the hollows directly. This is one of the frustrations of Mercury exploration. There are mysteries on the surface that demand physical investigation, that demand hands-on analysis, that demand someone to be there to touch the rock and measure it and tell us what it is made of. But Mercury is difficult. It is dangerous. It resists easy access. So we study it from a distance, and we infer, and we hypothesize, and we gather data through instruments that can only tell us so much. The hollows remain partially mysterious because the tools available, while sophisticated, are limited by their inability to directly sample the material. This limitation shapes how we understand Mercury. We know many things about it. We can measure, we can calculate, we can infer processes and mechanisms. But there are gaps in our knowledge where direct evidence would help tremendously. Mercury's atmosphere is gone. That is the simple statement, and it requires unpacking, because the absence of an atmosphere shapes everything about Mercury's present character, everything about how the planet exists now and how it will exist in the future. Mercury was not always atmosphereless. Planets form with primordial atmospheres, gas left over from the solar nebula, hydrogen and helium and other light elements that accumulate around planetary cores in sufficient quantities to create blankets of gas that hold heat and moderate conditions. But Mercury, so close to the Sun, so exposed to the solar wind, so assaulted by radiation, could not hold on to that atmosphere. The physics of atmospheric escape is fundamentally about energy and escape velocity. The Sun's gravity pulls less strongly on gas than on rock. Gas atoms are lighter and move faster than heavier particles. If a gas atom gains enough energy from solar radiation or collision, its velocity can exceed the escape velocity. Once that threshold is crossed, the atom flies away into space. There is no force pulling it back. It is gone. Heated by solar radiation and buffeted by solar wind particles, gradually escape becomes the rule rather than the exception. Over time, this escape accelerates. The more atmosphere is lost, the easier it is for the remaining atmosphere to escape. The density decreases, the thermal escape rate increases. Eventually, a tipping point is reached, where escape dominates over retention entirely. Mercury crossed that tipping point early in its history. The primordial atmosphere dissipated, likely rapidly and catastrophically. By the time Mercury had cooled enough to have a stable surface, the atmosphere was already mostly gone, vanished into space, lost forever. Some scientists believe that the escape was driven by the intensity of the young sun. The early sun in the first 100 million years of the solar system's existence was more active than it is now, had a more vigorous solar wind, produced more radiation. The conditions for atmospheric escape were perhaps dramatically more favorable then than they are now. The flux of solar energy would have been sufficient to heat the upper atmosphere to temperatures at which even heavy gases would have achieved escape velocity. Other scientists believe that impacts early in Mercury's history, during the heavy bombardment period when the inner solar system was still chaotic, might have stripped away the atmosphere. A massive collision could vaporize an atmosphere, blow it away entirely, convert it to vapor and kinetic energy that escapes into space. The exact mechanism remains debated, but the result is not. Mercury has no atmosphere. It never regained one. The conditions near the Sun are simply too harsh for an atmosphere to accumulate and persist. What Mercury has instead is an exosphere, which is almost the opposite of an atmosphere. An atmosphere is held in place by gravity. The molecules in an atmosphere collide with each other constantly, bouncing around, held down by the gravitational pull of the planet. Escape requires energy, requires heating to speeds high enough to overcome gravity's pull. An exosphere is a collection of atoms or molecules that are not gravitationally bound, that exist in the thin space near the surface, that are constantly being knocked off and lost to space without replacement at any significant rate. The exosphere is not generated by internal planetary processes. It is not outgassing from the interior. It is a surface phenomenon created by external bombardment. The exosphere is made of atoms blasted off the surface by impacts from micrometeorites and dust, particles falling from space that strike with tremendous velocity and scatter surface material. It is made of atoms knocked loose by the solar wind, charged particles flowing from the sun, striking the surface and dislodging material through direct collision and through electromagnetic effects. It is made of atoms released from the regolith, the surface dust, when solar radiation heats it, imparting energy sufficient for atoms to escape. It is made of atoms released through photochemical processes where ultraviolet radiation breaks chemical bonds and liberates individual atoms. The exosphere on Mercury is composed primarily of oxygen, sodium, hydrogen, helium, and potassium, elements that are either abundant in surface materials or that have been implanted by the solar wind. These atoms are sparse, extraordinarily sparse. They are not bound together by gravity or by molecular attraction. They are simply there, loosely associated with the planet, but constantly being lost to space. The exosphere has a scale height measured in hundreds of kilometers, meaning that the density drops off very rapidly as you move away from the surface. Just a few hundred kilometers above Mercury's surface, the exosphere transitions into the vacuum of space. The transition is not sharp, but the density gradient is steep. At 1,000 kilometers altitude, the exosphere is essentially gone. Yet even this tenuous exosphere is important to Mercury's overall system. It interacts with the solar wind. It affects how charged particles from the Sun interact with Mercury's surface. It provides a buffer zone where solar wind particles can be absorbed or deflected before striking the solid surface. It plays a role in the chemistry of the upper atmosphere, though chemical reactions are rare in such a dilute environment. The exosphere is Mercury's last tie to having an atmosphere at all. It is a shadow of what was. It is a reminder that Mercury once had something denser, something richer, something that could have sustained geological processes different from what exists now, something that could have created weather and wind and rain and all the processes that shape atmosphered worlds. But that is the past. Present day. Mercury has no real atmosphere, which means no weather, no wind patterns, no air currents carrying heat or dust, no circulation of energy around the planet. The sky is always black, the sun is always visible, except during twilight periods, when the observer is in shadow, but the sun is still above the horizon, illuminating the upper exosphere. The stars are visible at all times because there is no atmospheric scattering to obscure them. Standing on Mercury during the day would be a surreal experience, utterly alien to human sensory expectations. The sun would be brilliantly bright, much brighter than it appears from Earth, because Mercury is so much closer, dominating the sky with its intensity. The rest of the sky would be black, deep black, the black of space. Stars would twinkle overhead, their light unimpeded by any atmosphere. The temperature would be baking, extreme, dangerous. The radiation would be direct and unfiltered, bypassing any atmospheric protection. There would be no sound because sound requires a medium to travel through, and there is no air. The entire experience would be one of absolute isolation, of standing on a dead world under a black sky, exposed to radiation and heat and vacuum in equal measure, with only the thin exosphere between the regolith and the hard vacuum of space. The absence of an atmosphere also means that Mercury's geological surface is directly exposed to space in its entirety. Cosmic rays strike the surface constantly. The solar wind continuously scours the regolith, carrying away light elements and modifying surface chemistry. This weathering process, operating over billions of years, has profoundly modified the surface composition. The regolith has been broken down into extremely fine dust through repeated impacts and solar wind sputtering. The larger rocks have been pulverized and fractured by impacts and thermal stress, creating a layer of debris that coats the underlying bedrock. The exposed surface has been altered by space weathering, a process that is fundamentally different from weathering on atmosphered worlds. Space weathering change is the optical properties of rocks, making older surfaces darker and redder than fresh surfaces because of the accumulation of nanophase ion particles created by solar wind interactions. The space weathering on Mercury is particularly intense because Mercury receives no atmospheric protection whatsoever. There is no filtering of ultraviolet radiation. There is no shielding from the solar wind. The weathering extends deeper into the regolith because there is no atmosphere to shield the subsurface from radiation. The solar wind penetrates tens to hundreds of meters into the regolith, depending on the permeability of the material. The cumulative effect is that Mercury's surface has been transformed into a fine powder of broken rock and space-weathered dust. A regolith that bears little resemblance to the original rocks beneath it. Fresh impact craters expose unweathered material, bright material that has not yet been darkened by space weathering. These fresh craters stand out distinctly against the surrounding older, darker terrain. The contrast between fresh and weathered surfaces provides a chronological record. Younger surfaces are brighter, older surfaces are darker. The brightness of the hollows discussed earlier is partly due to their youth, partly due to the processes that create them exposing fresh material, and partly due to their composition, which may be intrinsically more reflective than the surrounding space-weathered regolith. Despite Mercury having no substantial magnetic field, until scientists realized it had one, the planet's magnetic field is real, measurable, and mysterious in ways that continue to perplex planetary scientists. Mercury has a global magnetic field. This fact alone should seem impossible given Mercury's small size and slow rotation. A magnetic field is generated by a moving liquid core, by the circulation of electrically conductive material inside the planet. The circulation creates a dynamo effect, where moving magnetic material regenerates and amplifies the field. Mercury's core is large and iron-rich, comprising about 2/3 of the planet's mass. It should have a magnetic field. It does have a magnetic field, but the strength of Mercury's magnetic field is only about 1.1% the strength of Earth's magnetic field. Given Mercury's composition, given the size and iron content of its core, the magnetic field should be roughly 30 times stronger than what we actually observe. If Mercury had a dynamo operating at the efficiency of Earth's dynamo, the field would be orders of magnitude stronger. The weakness of the field is paradoxical. It is one of the great mysteries of Mercury's geophysics, and one of the most studied aspects of the planet's interior. Mariner 10, the first spacecraft to visit Mercury in 1974 and 1975, detected the magnetic field. Instruments on board measured it precisely. The measurements left no doubt that Mercury has a global dipolar magnetic field, aligned roughly with the planet's axis of rotation, but only about 300 nanotesla in strength at the equator. That is weak by planetary standards. Earth's magnetic field is approximately 30,000 nanotesla at the equator, roughly 100 times stronger. Venus has no measurable global magnetic field, despite being similar in size to Earth. Mars has only weak, patchy magnetic field remnants from its past, relics of a time when the Martian dynamo was still operating billions of years ago. Mercury is the only other rocky planet besides Earth to have a global field currently operating. Yet Mercury's field is so feeble compared to what its composition should produce that scientists have spent decades trying to explain the discrepancy. The mystery deepened when later spacecraft visits provided more detailed measurements. MESSENGER, orbiting Mercury from 2011 to 2015, mapped the magnetic field in detail. The field was confirmed to be dipolar and global, but it remained weak, weaker than dynamical models predicted it should be. One leading explanation involves the solar wind and its suppressive effect on Mercury's magnetic field. The solar wind, the constant stream of charged particles flowing outward from the Sun, interacts with Mercury's magnetic field and shapes it in fundamental ways. Mercury's magnetosphere, the region of space around Mercury where the magnetic field dominates over external forces, is extremely small and extremely dynamic. It is only about 5% the size of Earth's magnetosphere. The reason for its small size is the solar wind pressure. Mercury is so close to the Sun that the solar wind is still fresh and vigorous, having not dissipated through a large distance like the solar wind that reaches Earth. The solar wind pressure at Mercury is roughly 9 times stronger than at Earth. This pressure compresses Mercury's magnetosphere, squeezes it, makes it smaller than it would be in the absence of such pressure. The magnetosphere's boundary, called the magnetopause, is pushed inward by the solar wind pressure. Under normal conditions, the magnetopause sits only a few Mercury radii above the equator, meaning the protective bubble extends only a short distance above the surface. A disturbance in the solar wind can push it even closer. During coronal mass ejections, when the Sun ejects massive quantities of plasma and magnetic field in giant eruptions, the magnetopause can be compressed right down to Mercury's surface. When that happens, the solar wind can interact directly with the planet's surface. Particles can strike the regolith unimpeded. Chemical reactions can occur between the solar wind particles and the surface materials. The effects can be observed in how the surface composition changes, how atoms are driven off, how the regolith is modified. The theory is that this constant bombardment and compression by the solar wind may actually suppress the growth of Mercury's magnetic field. The field has reached an equilibrium state where the solar wind interaction prevents amplification. The dynamo in the core continues to operate and maintains a field, but the field does not grow stronger because external forces limit its extent. This dynamic interaction between Mercury's magnetic field and the solar wind may actually suppress the field from being stronger than it currently is. The theory is that the solar wind interaction prevents the magnetic field from amplifying through normal dynamo processes. Instead of growing stronger over time, as might be expected if the core was simply hot and convecting, the field remains suppressed by external factors. The field that we measure is in a state of dynamic equilibrium with the solar wind. Change the solar wind conditions, and the field changes in response. The magnetosphere shrinks and expands with solar wind variations. The field responds on timescales of minutes to hours, extraordinarily rapid by comparison to Earth's magnetosphere. This interaction is one of Mercury's most distinctive features. Mercury exists in a unique region of space where the solar wind is still strong, but Mercury is also small and has its own magnetic field. The interaction between these factors creates phenomena that do not occur anywhere else in the solar system. Mercury's magnetic field, weak though it is, still provides some protection for the exosphere. The field channels the solar wind around the planet rather than allowing it to strike the surface directly everywhere. In certain regions called the cusps, where the magnetic field geometry allows solar wind particles to approach the surface, the interaction is intense. The cusps are where the most vigorous interaction occurs between Mercury's space environment and its surface. They are regions of activity and change, marked by distinctive patterns in how particles interact with the regolith and how atoms are sputtered away. The cusps represent the most dynamic parts of Mercury's magnetosphere, where the protective effect of the field breaks down and the solar wind has direct access to the surface. The weakness of Mercury's magnetic field raises profound questions about the nature of the core itself and the future of Mercury's magnetic environment. If the core is cooling, if the liquid portion is slowly solidifying, then the dynamo that generates the field should be weakening and eventually ceasing. Yet the field persists in the present. Thermal models of Mercury's core suggest that there should still be enough heat to maintain a liquid outer core, but just barely, precariously, on the edge of complete solidification. The core is cooling inexorably. Mercury's interior is gradually losing heat to space. Billions of years from now, the core will be completely solid, the dynamo will cease, and the magnetic field will vanish entirely. Mercury will become a world with no magnetosphere, completely exposed to the solar wind. But for now, in the present era, the field remains. The presence of a partially molten core is itself a surprise and a puzzle. A small planet should have cooled and solidified completely by now. Our models of planetary cooling suggest that a body the size of Mercury should be frozen solid after 4.5 billion years of cooling. The fact that Mercury's core is still partially liquid suggests either that the core has a high concentration of light elements like sulfur that lower its melting point, allowing material to remain liquid at lower temperatures, or that some source of heat is keeping the core warm enough to maintain fluidity. Tidal heating from the eccentric orbit may contribute significantly. The gravitational flexing of the planet by the sun's tidal forces generates heat that rises from the core toward the surface. Radioactive decay in the core and mantle may contribute as well, though the amount of radioactive material remaining is less than in the past. The combination of heat sources is sufficient to maintain the magnetic field, but barely, with little margin for error. Mercury's magnetosphere responds rapidly to changes in the solar wind, faster than any other planetary magnetosphere in the solar system. The timescale for the magnetosphere to respond to a disturbance is only 1 to 2 minutes. At Earth, the magnetosphere takes hours or even longer to fully respond to solar wind changes because Earth is larger and the processes operate on longer timescales. Mercury's small size and proximity to the Sun create a much more dynamic and responsive environment. The magnetosphere is constantly being buffeted and reshaped by solar wind variations. It is a thin, fragile structure separating Mercury from the direct impact of the solar wind. Without this field, the solar wind would strike Mercury's surface unimpeded. The regolith would be scoured much more vigorously. The exosphere might be denser if not for the magnetic field's protection. The composition of the surface and exosphere might be significantly different. The field, weak though it is, still matters profoundly for Mercury's overall space environment and surface interactions. Ice on Mercury is contradictory, impossible, and real. Mercury is the closest planet to the Sun, bathed in solar radiation. Its daytime surface temperatures reach 430 degrees Celsius, hot enough to melt lead, hot enough to vaporize water explosively if it existed in liquid form on the sunlit surface. Yet Mercury has water ice, not just a little ice, not a trace amount. Substantial deposits of water ice, billions of tons of it, concentrated at the poles, hidden in permanently shadowed craters that never see sunlight under any circumstances. The ice was discovered by radar observations from Earth conducted in the late 20th century and confirmed by subsequent spacecraft observations. The radar signals bounced off Mercury's polar regions and returned with signatures that matched water ice. Exactly. When scientists saw those signatures, they initially doubted them. How could there be ice on the hottest planet relative to the Sun? How could ice persist in such a hostile environment? But the evidence was unambiguous. Subsequent observations by instruments sensitive to neutrons, which are absorbed by hydrogen-bearing materials like water, confirmed that hydrogen was present in large concentrations in the polar regions. Neutron spectrometers on spacecraft measured the absorption pattern. The data matched the expected signature for water ice. The ice is real. The paradox of ice on Mercury drove researchers to understand the mechanism that allowed it to persist. The answer lies in Mercury's geometry and orbital mechanics. The coldest places on Mercury, the permanently shadowed craters at the poles, never receive direct solar radiation under any circumstances. Mercury's minimal axial tilt, only 2 degrees compared to Earth's 23.5 degrees, means that the poles remain in perpetual twilight, neither in direct sunlight nor in complete darkness. The sun never rises high enough above the horizon at the poles to illuminate certain crater floors. Craters at the poles, particularly the deepest craters with overhanging rims and complex topography, remain permanently shadowed. These shadowed crater floors never face the sun directly. The temperature in these craters is maintained at a frigid -170 to -180 degrees Celsius, far below the temperature at which water or ice can sublimate into vapor. At such cold temperatures, ice is incredibly stable. Sublimation requires input of energy, and that energy is not available in the perpetual shadow. This temperature is stable and permanent because the craters never receive sunlight and Mercury's orbit and rotation remain steady. The surrounding region, where sunlight penetrates, remains at much higher temperatures, hot enough to make the contrast extreme. But inside the perpetually dark crater floors, it is always cold. The ice accumulates and persists. Once ice has been delivered to these cold regions, it stays. It does not evaporate. It does not sublimate. It is trapped in a state of permanent preservation. The origin of Mercury's polar ice remains uncertain, one of the remaining mysteries about how water came to exist on such a hot world. Water is not manufactured on Mercury in any significant quantities. There is no mechanism to produce water through geological processes operating on Mercury's surface and interior. The ice must have come from somewhere else, delivered from external sources. The most likely source is comets and asteroids that impacted Mercury early in the solar system's history, particularly during the heavy bombardment period when the inner solar system was chaotic and collisions were frequent. Comets and some asteroids contain substantial quantities of water ice, along with rocky material. When they struck Mercury, traveling at tens of kilometers per second, the impacts would have been violent. Much of the ice would have vaporized from the heat of impact, converting from solid ice to water vapor that expanded explosively away from the impact site. Some of the ice, however, might have survived the impact or been incorporated into the regolith without being completely vaporized. If water vapor was produced during impacts and then rose into Mercury's thin exosphere, some of it could have drifted toward the poles where the cold would cause it to condense back into ice. This condensation could have occurred repeatedly as new impacts delivered more water vapor. Over billions of years, this process could have accumulated significant quantities of ice in the permanently cold polar regions. Another possibility is that the water was produced through chemical reactions right on Mercury's surface. The solar wind, the stream of protons and other particles flowing from the sun continuously strikes Mercury's surface. These particles can react with oxygen-bearing minerals to produce water molecules. The reaction is not efficient, producing water in small quantities for each impact, but the process is continuous and relentless. Over billions of years, trillions of impacts might produce substantial quantities of water, molecule by molecule, deposited in the regolith. Water molecules produced this way could gradually migrate to the cold poles through slow diffusion through the regolith, accumulating in the shadowed regions where they freeze into ice. A combination of both processes might operate simultaneously. The total amount of ice at Mercury's poles is substantial by any standard. Estimates suggest that there are billions of tons of water ice, possibly on the order of 100 billion tons or more. This is more water ice than exists in some of the icy moons of the outer solar system. This ice is preserved not by cold in the conventional sense, as we think of it on worlds like Europa or Enceladus, but by the geometric properties of the craters and the orbital mechanics that keep the poles in shadow, that keep them isolated from solar radiation, that ensure they remain cold forever as long as Mercury orbits the Sun and maintains its current axial tilt. The presence of ice at the poles is scientifically important for several compelling reasons that extend from planetary science to astrobiology to human exploration. First, it demonstrates that the temperature conditions on Mercury are extreme enough to maintain stable ice in specific locations despite the proximity to the Sun. The combination of minimal axial tilt and crater geometry creates a special case where ice can persist where intuition suggests it should not. This finding expanded scientists' understanding of where ice could exist in the solar system. It suggested that even close to the Sun, under the right geometric and thermal conditions, ice could remain frozen. Second, the ice potentially contains records of Mercury's early history encoded in isotopic signatures. If the ice formed early from impacting bodies and remained relatively undisturbed since formation, the isotopic ratios of hydrogen and oxygen in the water molecules would reflect the composition of the impacting bodies. Scientists can study the ice to learn about the composition and origin of the asteroids and comets that bombarded Mercury billions of years ago. The ice is a time capsule, a preserved sample of material from the early solar system. Third, the ice represents a potential resource if humans ever establish operations on Mercury. Water is essential for life support in any permanent human settlement. Water can be split into hydrogen and oxygen, providing rocket fuel and oxidize. Having a water source on Mercury accessible to human explorers would be extraordinarily valuable for any long-term presence. The ice at the poles could enable human exploration that would otherwise require bringing all water from Earth at enormous cost. Fourth, the ice on Mercury provides insights into other bodies in the solar system. If ice can persist on Mercury in shadowed regions, the same mechanism might apply elsewhere. The Moon has polar ice in shadowed craters. Mars has ice at the poles. Understanding Mercury's ice helps scientists understand ice preservation mechanisms across the solar system. The discovery of ice on Mercury changed how scientists view the planet fundamentally. It is not simply a dead, sterile rock baked by the Sun. It has complexity. It has variation. It has regions where ice persists in places where intuitively it should not exist, where common sense suggests nothing frozen could survive. Mercury demonstrated that planetary systems are more nuanced than simple models suggest. Looking at Mercury from Earth in ancient times, observers saw something strange and unsettling. The planet never strayed far from the Sun in the sky. It appeared only briefly at dawn or dusk, never high in the night sky. It moved erratically, appearing and disappearing according to patterns that seemed chaotic to early astronomers. Some ancient observers believed Mercury was two different objects, one visible at sunrise and one at sunset, that happened to follow similar paths. Others eventually recognized it as a single planet bound to the Sun's position. The name Mercury came from the Roman god of commerce and messages, fitting for a swift planet. Mercury was important to ancient astronomers because understanding its erratic motion was crucial to developing planetary models. The Ptolemaic model, centered on the Earth, explained Mercury's motion through epicycles, circles upon circles. Mercury orbited on a small epicycle that itself orbited the Earth, an arrangement that approximated the observed behavior well enough for the time. As observations improved, Mercury remained difficult to model precisely within any geocentric framework. The Renaissance brought improved astronomical instruments and telescopes appearing in the early 1600s. Galileo observed Mercury and discovered it displayed phases, like the Moon, growing large, then diminishing. This phasing could only occur if Mercury orbited the Sun, not the Earth. When Mercury is between Earth and the Sun, only a crescent is visible. When on the far side of the Sun, it appears nearly full. This observation provided powerful evidence for the heliocentric model, though it was not immediately controversial like Jupiter's moons. Mercury's phases demonstrated that Mercury orbited the Sun, a crucial piece of evidence that helped shift astronomical thinking toward heliocentrism. Detailed observations of Mercury from Earth remained difficult for centuries. The planet is small and always near the Sun, making observation challenging. Twilight obscures dim objects near the Sun, and the Sun's bright light overwhelms the faint light reflected by Mercury. Some observers claim to see surface features suggesting rotation, but distinguishing real features from observational artifacts proved difficult. The true rotation period remained unknown until radar astronomy emerged in the mid-20th century. Radar could penetrate atmospheric distortion and measure Mercury's surface properties directly. Radar observations in the 1960s, using large radio telescopes, finally measured Mercury's rotation period definitively, 59 Earth days. This period stood in a precise mathematical relationship to the orbital period of 88 days. Mercury rotates 3 times for every 2 orbits, a 3-to-2 resonance that is exact and demonstrable. The relationship was remarkable and unexpected. The 3-to-2 resonance was shocking to astronomers because it seemed to require explanation. Why would Mercury rotate at this exact rate? Initial hypotheses suggested Mercury had been tidally locked in the past and then spun up to its current rate. But calculations showed the 3-to-2 resonance was actually stable. The orbital dynamics and tidal interactions created a state of equilibrium. Mercury was locked into the 3-to-2 resonance permanently. The eccentricity of Mercury's orbit and the strength of tidal forces created conditions where the 3-to-2 ratio was gravitationally stable. Any small perturbation would be damped out by tidal interactions. The resonance was not accidental, but a configuration maintained by orbital physics. Understanding the 3-to-2 resonance required understanding tidal mechanics. The Sun's gravity pulls Mercury unevenly. This differential pull creates a torque on Mercury's body. Because of Mercury's orbital eccentricity, the tidal torque varies throughout the orbit. When Mercury is closest to the Sun, the torque is strongest. The combined effect of varying torques creates a resonance condition. The 3-to-2 ratio is the stable resonance for Mercury's orbital parameters. The tidal forces naturally drive and maintain this resonance. The discovery demonstrated that gravitational interactions could explain Mercury's rotation, and that patterns persist over billions of years. This discovery was made from Earth using radio telescopes without a spacecraft orbiting Mercury. Radar signals bounced off the surface, and returning echoes carried rotation information encoded in the Doppler shift. Different parts of Mercury's rotating surface have different velocities, creating radar frequency shifts. By analyzing the echoes, astronomers determined the rotation rate. Radar astronomy proved to be a powerful tool for studying solar system objects, providing information impossible through telescopic observation alone. The measurement represented a shift in planetary science, combining ground-based radar with advancing spacecraft capabilities to create a comprehensive understanding of Mercury. But radar from Earth had limitations. The signals were weak. The measurements had uncertainty. Direct observation required getting closer, required sending spacecraft to investigate, required traveling through the harsh environment near the Sun to conduct proper science. And that is exactly what NASA decided to do in the early 1970s, when it launched Mariner 10, the first spacecraft to visit Mercury in human history. Mariner 10 represented a bold leap forward. The spacecraft was not built specifically for Mercury. It was designed as a versatile probe, capable of visiting multiple planets in a single mission. The Mariner program had already sent successful spacecraft to Venus and Mars. Now NASA would extend the program further inward, toward the Sun, into hotter regions, toward a destination that presented challenges unlike anything encountered before. The engineering required to send a spacecraft to Mercury was extraordinary. The proximity to the Sun meant intense solar radiation that would heat the spacecraft. Solar panels, the standard way to power spacecraft, would generate too much excess heat if exposed directly. Mariner 10 was designed with reflective surfaces to minimize heat absorption. Heat radiators were incorporated to reject excess thermal energy. The spacecraft had to be tough, resilient, and capable of surviving conditions that would destroy conventional equipment. Mariner 10 launched from Earth on November 3, 1973. The mission plan was audacious. The spacecraft would first fly to Venus, use Venus's gravity to redirect its trajectory toward Mercury in what is called a gravitational assist or slingshot maneuver. This technique allowed the spacecraft to gain speed without consuming additional fuel, a clever solution to the problem of reaching a destination that requires tremendous velocity to approach. After the Venus flyby, Mariner 10 would continue toward Mercury, encounter the planet, conduct observations, and return data to Earth. The spacecraft carried instruments designed to image Mercury's surface, measure its magnetic field, analyze the composition of the exosphere, and take precise measurements of the planet's physical properties. Scientists were eager. Mercury had remained largely mysterious. Ground-based observations and radar data had revealed some properties, but there were gaps, uncertainties, questions that demanded direct observation. The spacecraft itself was relatively small by modern standards, about 1.2 meters long, weighing roughly 360 kilograms. Every component had to function perfectly in an environment more hostile than any previous spacecraft had encountered. The solar panels had to survive intense heat while still generating power. The radio transmitter had to send signals across tens of millions of kilometers with sufficient strength that Earth could detect them. The instruments had to collect data in conditions that would damage less robust equipment. The engineering challenge was formidable, but NASA's engineers and contractors rose to meet it. Mariner 10 reached Venus on February 5, 1974, conducting a close flyby that allowed the spacecraft to photograph the planet's atmosphere and measure its properties. The gravity of Venus bent the spacecraft's trajectory precisely as calculated, redirecting it toward Mercury. The spacecraft continued its journey, traveling deeper into the solar system, approaching Mercury from the outer system. On March 29, 1974, Mariner 10 made its first encounter with Mercury. The spacecraft passed within 704 kilometers of Mercury's surface. It was the closest approach any human-made object had come to Mercury. The instruments activated. Cameras began photographing. The magnetic field instruments took readings. The plasma sensors measured the exosphere. Data flowed back to Earth at the speed of light, information encoded in radio signals that traveled across the void, carrying humanity's first detailed view of Mercury from up close. The images that returned showed a landscape that astonished scientists who had speculated about Mercury's surface for decades. The cratering was extensive and complex. Large craters, small craters, overlapping craters, craters within craters, a geological record written in impact scars. The Caloris Basin dominated the imagery, its massive concentric rings and surrounding terrain revealing the magnitude of the collision that created it. The terrain appeared ancient, geologically stable, a landscape that had been battered and then left largely undisturbed for billions of years. What Mariner 10 revealed transformed understanding of Mercury. The images showed a cratered surface resembling the Moon, heavily marked by impact craters of various sizes. The photographs revealed the Caloris Basin, that enormous impact feature that dominates Mercury's geology. The images showed wrinkle ridges, scarps, and other features created by Mercury's internal cooling and contraction. The magnetic field measurements confirmed that Mercury had a global magnetic field, surprising given the planet's small size and slow rotation. The exosphere measurements detected sodium, potassium, and other elements in the thin gas surrounding the planet. The data was rich and detailed, but Mariner 10 was not finished. The spacecraft's trajectory allowed it to encounter Mercury again. On September 21, 1974, Mariner 10 made a second pass, flying even closer this time, within 480 kilometers of the surface. The encounter provided additional images and measurements, filling in details and confirming observations from the first pass. Then came a third encounter on March 16, 1975. The spacecraft had fuel and trajectory options, and NASA approved another close passage. Mariner 10 flew within 327 kilometers of Mercury, obtaining even more detailed imagery of regions previously imaged or not imaged at all. The three encounters allowed Mariner 10 to map a significant portion of Mercury's surface, but not the entire planet. Due to Mercury's rotation and the geometry of the spacecraft's trajectory, Mariner 10 could only image roughly 45% of Mercury's surface. The other half remained hidden from view. This limitation shaped future exploration. Scientists knew Mercury better after Mariner 10, but they also knew how much more remained unknown. The detailed images of craters, the measurements of the magnetic field, the detection of the exosphere, all provided insights that fundamentally changed how Mercury was understood. But the data also raised new questions. Why was the magnetic field so weak? What was the composition of the surface? How did those wrinkle ridges form? What was the history of volcanic activity? The mysteries deepened even as answers accumulated. After Mariner 10's final encounter in 1975, the spacecraft continued its orbit around the Sun, useful data transmitted, but the mission ended. No spacecraft returned to Mercury. The planet receded from attention. The focus of planetary exploration shifted. Voyager probes launched toward the outer planets. Shuttle flights began. Resources were allocated to other missions. Mercury faded into the background of scientific consciousness, studied through analysis of Mariner 10 data, but not visited again. The gap lasted decades. 40 years passed. An entire generation of scientists trained, conducted research, and retired without seeing new Mercury data from spacecraft. Postdoctoral researchers became full professors who trained students who became scientists themselves, all working in a world where Mercury remained known only through images taken in 1974 and 1975. What was learned from Mariner 10 was studied exhaustively. Every image was examined repeatedly. Every measurement was analyzed from multiple perspectives. Entire research careers were built on interpretations of Mariner 10 data. But there was only so much that could be extracted from data collected in the early 1970s. The images had a limited resolution. The instruments measured crude parameters by modern standards. New questions accumulated. Technology improved exponentially. Scientists developed better instruments that could measure things previously unmeasurable. The hunger to return to Mercury grew, but the will to actually send a mission took far longer to materialize. Why did exploration of Mercury stall for so long? The reasons were multiple and deeply rooted in the practical realities of space exploration. Mercury is difficult to reach. The proximity to the Sun makes the mission hazardous in ways that Venus or Mars do not present. Solar radiation and heat pose extraordinary engineering challenges. Any spacecraft must be robust, with shielding and thermal management systems that work reliably in an environment of intense solar flux. Launching spacecraft when planets are not well aligned is wasteful of fuel and time. The alignment of Earth and Mercury for efficient spacecraft transfer occurs infrequently, on timescales measured in years. Missions had to be planned carefully around these windows of opportunity. Competing priorities claimed resources. In the 1970s and 1980s, the outer planets seemed more intriguing. Jupiter had moons that resembled worlds, with signs of geological activity and unusual properties. Saturn had rings that captivated the imagination, and moons that seemed exotic and mysterious. Mars seemed more accessible, more close to Earth in spirit, a destination where humans might eventually walk. Uranus and Neptune were completely unknown before the Voyager probes, their moons and systems providing years of discovery and research questions. These destinations captured imagination and funding in ways that Mercury did not. Mercury remained in the background, a world that had been visited once and seemed less urgent than the beckoning mysteries of the outer solar system. The funding for planetary exploration, limited in absolute terms, was allocated toward destinations that seemed to offer more insights, more novelty, more potential for major discoveries. But some scientists never stopped thinking about Mercury. They understood that the planet held key insights into planetary formation, into how planets acquired their properties, into the nature of bodies close to stars. They pushed for a new mission. The idea evolved through discussions, proposals, and refinements, a process that took years and required convincing space agencies that Mercury was worth the investment. Eventually, after prolonged advocacy and persuasive presentations, NASA approved a new Mercury mission. This spacecraft would be called Messenger, which stood for Mercury's surface, space environment, geochemistry, and ranging. The mission was approved in 1999. Construction began. The spacecraft was built with advanced instruments reflecting the technological progress of 2 decades since Mariner 10. The engineering was more sophisticated, the instruments more capable, the science more ambitious. Messenger would carry an imaging system that could photograph Mercury in multiple wavelengths, revealing compositional information that simple black and white photography could not provide. It would carry spectrometers that could analyze the light reflected by Mercury's surface with high spectral resolution, determining what elements were present and how they were distributed across the surface. It would carry magnetometers that could measure the magnetic field in greater detail than Mariner 10 could achieve, resolving smaller scale variations and variations that changed on shorter timescales. It would carry instruments to measure the exosphere more precisely, detecting sodium, potassium, and other elements that compose this thin gas surrounding Mercury. It would carry instruments to measure neutrons, which would indicate the presence of hydrogen, which would reveal where water ice might exist, a discovery that would have seemed impossible in the Mariner 10 era, but that Earth-based radar had hinted might be possible. Messenger launched on August 3, 2004. The spacecraft was on a long journey. It could not travel directly to Mercury. The spacecraft required a series of gravitational assists to reach Mercury's orbit efficiently. Messenger flew past Earth once, passed Venus twice, and passed Mercury multiple times before achieving a stable orbit around the planet. The first Mercury flyby occurred on January 14, 2008. Messenger passed within 198 kilometers of the surface. The spacecraft was approaching Mercury for the first time, and the instruments revealed features that had changed the understanding of the planet. The gravity measurements showed that Mercury's moment of inertia, a fundamental property related to how mass is distributed inside the planet, was different from what scientists expected. The moment of inertia was smaller than models predicted, suggesting that Mercury's core was larger and denser than previously thought. This measurement had profound implications. It meant Mercury's internal structure was extreme, even compared to what Mariner 10 data had suggested. Messenger made 2 more flybys before achieving orbital insertion on March 17, 2011. The spacecraft was now in orbit around Mercury, the second spacecraft ever to reach the planet, approaching from a new era of technology and measurement capability. The mission began its systematic study of Mercury. The spacecraft would orbit the planet for 4 years, collecting data continuously. The instruments would photograph Mercury multiple times, building a complete map of the entire planet's surface. Every feature would be imaged. Every region previously hidden would be revealed. The compositional data would show what Mercury was made of. The magnetic field measurements would map the field in detail. The exosphere measurements would show where the different atmospheric elements were concentrated. The gravity measurements would reveal internal structure. What Messenger revealed transformed Mercury science in ways that scientists had not fully anticipated. The complete mapping showed a planet more complex and geologically active than Mariner 10 imagery suggested. The cratering record was more detailed, showing subtle differences in crater characteristics across different regions that spoke to compositional variations. The volcanic features were better understood, with smooth plains clearly visible and bearing characteristics consistent with lava flows. The wrinkle ridges that track Mercury's contraction were mapped completely, showing a global pattern of contraction that spoke to the planet's internal cooling and shrinking. But the most surprising discoveries involved specific features and phenomena that had not been clearly identified in Mariner 10 data before. The hollows, those bright, reflective deposits scattered across Mercury's surface, were imaged in detail by Messenger cameras with unprecedented resolution. What were they made of? The composition was puzzling and contentious among researchers. They were too bright to be normal rock. They seemed to be concentrated in certain regions, particularly in the walls of impact craters and along certain geological features. They appeared freshly exposed, geologically young, with no visible impact craters on top of them that would suggest they were ancient. Their origin and composition became a major research question that drove significant discussion and debate in the scientific community. Some researchers proposed they were exposed metallic minerals. Others suggested sulfur compounds or other exotic, icy materials. The hollows remained partially mysterious despite Messenger's detailed observations, a puzzle that continues to drive research today. The water ice at the poles, detected by Earth-based radar, was confirmed definitively by Messenger measurements. Messenger carried instruments that could detect neutrons, particles produced by cosmic rays striking the surface. Water ice absorbs neutrons, creating a distinctive pattern in the neutron measurements. The measurements confirmed that there were billions of tons of ice at Mercury's poles, more extensive and concentrated than previous Earth-based estimates had suggested. The discovery was scientifically profound. Ice was not supposed to exist on Mercury in significant quantities. Yet here it was, accumulating and persisting in regions that never saw direct sunlight. The discovery raised profound questions about how ice could persist on such a hot world, questions that drove investigation into the geometry of the polar craters and the thermal conditions they maintained. The magnetic field measurements confirmed that Mercury's field was weak, much weaker than a planet of Mercury's composition should produce. The field was also offset from Mercury's center, not aligned with the planet's axis of rotation. This offset was unexpected and significant. It suggested that Mercury's magnetic field had properties unlike other planetary fields. The solar-wind interactions were measured in detail. The magnetosphere was far more dynamic than anticipated. Coronal mass ejections from the Sun compressed the magnetosphere dramatically. The solar-wind interaction was intense and continuous, with time-varying patterns that responded to changes in the solar wind conditions on timescales of minutes. Messenger also discovered something unexpected about Mercury's geological history. The planet showed evidence of recent volcanic activity, much more recent than scientists had expected. Some volcanic features appeared young, geologically fresh. Some scarps that resulted from Mercury's contraction appeared very young, too recent to have formed billions of years ago. This suggested that Mercury was not a dead world, as some had assumed. Geological processes continue to shape the planet today. The data revealed Mercury's tilted magnetic field in detail. Unlike Earth's magnetic field, which aligns roughly with the rotation axis, Mercury's magnetic field was offset. The magnetic equator did not coincide with the geographical equator. This offset was small, but real and significant. It suggested something unusual about Mercury's core, or the dynamo processes generating the field. Scientists debated the implications. The measurements opened new areas of investigation. Messenger also took extremely detailed gravity measurements using radio tracking. The gravitational field of a planet reveals how mass is distributed inside it. Variations in the gravitational field indicate denser or less dense regions. The gravity data confirmed that Mercury's core was extraordinarily large, even larger than Mariner 10 data had suggested. The core was also dense, more iron-rich than any other terrestrial planet. This composition was puzzling. How did Mercury acquire such a large iron core? The question drove discussion about Mercury's formation. Did Mercury form from different materials than other terrestrial planets? Was Mercury struck by a giant impact early in its history that stripped away much of its rocky mantle, leaving a core-dominated body? The gravity measurements provided clues, but not definitive answers. Messenger's 4-year mission produced an extraordinary dataset. The spacecraft collected data continuously, building maps, taking measurements, providing insights into every aspect of Mercury's properties and environment. The mission was extended beyond the initial 4-year plan. The spacecraft continued operations. Additional data accumulated. The mission continued until Messenger's fuel was depleted. By 2015, the spacecraft was no longer capable of maneuvering. It had no way to maintain its orbit indefinitely. The inevitable conclusion approached. Messenger was directed to crash into Mercury deliberately on April 30th, 2015. The impact was controlled, happening on the far side of Mercury from Earth, not observable directly. But the impact served a purpose. Scientists could use the impact timing and the disruption of the spacecraft's radio signal to make precise measurements of Mercury's gravity field. The measurement was one final piece of data from a mission that had revolutionized Mercury science. The data from Messenger transformed Mercury from a mysterious world visited once in the 1970s into a place where detailed science was possible. Complete surface mapping provided context for understanding features. Compositional data revealed what Mercury was made of. Magnetic field measurements mapped the field comprehensively. The exosphere was measured in detail. The polar ice was confirmed and studied. The core was shown to be extraordinarily large and dense. The surface was shown to be younger than expected, with ongoing geological processes. The mission answered many questions, but it also created new mysteries and opened new areas of investigation. Scientists were hungry for more information. A new mission was already in development. Bepi Colombo is the current mission to Mercury, a joint effort between the European Space Agency and the Japanese Aerospace Exploration Agency. The spacecraft launched from Earth on October 20th, 2018. The mission name itself is a tribute to Giuseppe Colombo, an Italian scientist who made fundamental contributions to understanding Mercury's orbital mechanics and rotation characteristics. The mission is more ambitious than Messenger in its scope and its architecture. Two separate spacecraft are involved working in concert. One is an orbiter designed to study Mercury's interior structure, surface composition, and exosphere in detail. The other is a small magnetometer orbiter designed specifically to study Mercury's magnetic field in unprecedented detail, making measurements that Messenger could not achieve. The two spacecraft will operate together, providing complementary measurements that address different scientific questions. The journey to Mercury is long and complex. Bepi Colombo cannot travel directly from Earth to Mercury using a straightforward trajectory. The spacecraft requires gravitational assists from Earth, Venus, and Mercury multiple times to reach its destination and achieve its final orbital configuration. This indirect route, while seemingly inefficient, allows the spacecraft to shed velocity gradually and arrive at Mercury with the correct orbital parameters. The spacecraft made flybys of Earth and Venus before its first Mercury encounter. The mission planned multiple Mercury flybys, carefully timed to gradually adjust the spacecraft's trajectory and velocity. The first Mercury flyby occurred on October 1st, 2021. The spacecraft passed within 2,000 kilometers of Mercury's surface, a distant approach compared to Messenger's closest distances, but sufficient for the instruments to begin taking data and test their systems in the Mercury environment. Additional flybys are planned, each bringing the spacecraft closer and adjusting its trajectory toward the final orbital configuration, where both spacecraft will separate and settle into their intended orbits. Bepi Colombo carries advanced instruments reflecting technological progress since Messenger's design. The imaging systems use new detector technology with superior sensitivity. The spectrometers can detect finer details in reflected light, operating across ultraviolet to infrared wavelengths. The magnetometers are more sensitive than Messenger's instruments, capable of measuring weaker variations in the magnetic field. The gamma-ray spectrometer can determine the elemental composition of the surface by detecting radiation produced when cosmic rays strike the surface. The neutron detector can measure the distribution of hydrogen across the entire planet with higher precision than Messenger achieved. The gravity measurements will be even more precise than Messenger's, using advanced radio tracking techniques and sophisticated data processing. The mission plan is ambitious and scientifically comprehensive. The spacecraft will achieve an orbit that allows it to study Mercury's north and south poles in detail, a capability that neither Mariner 10 nor Messenger fully possessed. Previous missions could not examine the poles closely because the orbital geometry did not allow close approaches to high latitudes. Bepi Colombo will change that, with specific orbital parameters designed to bring the spacecraft over the polar regions repeatedly. The ice at the poles will be studied in detail. The composition of the polar regions will be measured with spectroscopic instruments. The processes that maintain the ice in the presence of Mercury's heat will be investigated directly through long-term observations, tracking how the ice persists and whether it changes seasonally or over longer timescales. The magnetometer orbiter will measure Mercury's magnetic field with unprecedented precision, generating detailed maps that show how the field varies across the planet. The two-orbiter configuration will allow the field to be measured at different altitudes simultaneously, providing unique insights into how the field varies with altitude and what this tells us about the source of the field deep within Mercury's core. The mission is ongoing as of 2024. The spacecraft continues its journey toward Mercury. Additional flybys are scheduled. The mission timeline extends many years into the future. Once in final orbit, the spacecraft will operate for an extended period, collecting data continuously. The data will address questions raised by Messenger. It will provide insights into mysteries that remain unsolved. It will likely reveal new phenomena that will generate new questions. This is how planetary exploration works. One mission answers questions and raises new ones. The next mission addresses the new questions and discovers new mysteries. The cycle continues. Knowledge accumulates gradually. Understanding deepens incrementally. But each mission fundamentally changes how we comprehend the worlds we study. Mercury remains a world of mysteries despite decades of spacecraft investigation and thousands of scientific papers examining the data collected from orbital spacecraft. The questions are specific and compelling, the kind of questions that drive scientific research and drive funding requests for new missions. The magnetic field mystery persists as one of the most fundamental puzzles in Mercury science. Why is Mercury's field so weak? Only 1% the strength of Earth's, despite Mercury's composition, suggesting it should be much stronger. Why is the field offset from the rotation axis, creating an asymmetry that no simple model explains? What does this tell us about Mercury's core and the dynamo processes inside that generate the field? How much longer will the dynamo operate as the core slowly cools? Will the magnetic field continue to weaken as the core cools, eventually disappearing entirely? Bepi Colombo's detailed measurements may provide some answers, may reveal the source of the offset, may clarify the processes maintaining the field. But the core mystery of Mercury's unusual magnetic properties may persist even after the mission concludes, a fundamental question that might require new theories or new observations to answer. The hollows remain mysterious and controversial. What are they made of? Why are they so bright, brighter than any normal rock? How did they form? Are they still forming, or did they form only in the distant past? Some theories suggest they might be exposed metallic minerals, perhaps iron or some other metal exposed through erosion or other geological processes. Other theories propose sulfur compounds, exotic ices, or other materials. Some researchers propose they might be deposits left by comets or asteroids that struck Mercury. Others suggest volcanic processes create them. Direct sampling would definitively answer the question, would allow a scientist to take a sample in hand, examine it with all available tools, determine its composition definitively. But no sample return mission to Mercury is currently planned, and none seems likely in the near future, given the expense and technical challenges. The hollows will likely remain partially mysterious, their composition and origin a subject of study and debate, until some future mission brings samples back to Earth. The water-ice origin is partially understood, but not completely. Comets and asteroids may have delivered the ice. Solar wind reactions with surface materials may have produced some water. Both processes may operate simultaneously, but the exact contributions are uncertain. The timing of ice accumulation is unknown. Did most of the ice arrive early, during the heavy bombardment period, or does ice accumulate continuously through ongoing processes? The persistence of the ice is understood mechanically, but the overall origin story remains somewhat unclear. The shrinking of Mercury continues. The interior cools inexorably. The surface contracts. How much more shrinking will occur? How long until the core solidifies completely and the shrinking stops? How long until the magnetic field disappears? These timescales are measured in billions of years, but the processes are ongoing now. The weird terrain represents an impact of truly colossal proportions. The Caloris Basin itself is one of the largest impact features in the solar system. But what exactly happened when the impact shock waves converged on the opposite side? The terrain is not fully understood. Why is it so chaotic? What does the deformation pattern tell us about Mercury's interior structure? The surface composition has been measured, but compositional variability exists that is not yet fully explained. Different regions have different compositions. Some areas are richer in certain elements than others. The volcanic history is clearer than before, but questions remain about the timing and extent of volcanic activity. How long did volcanism persist? When did it end? The polar regions remain largely unmapped by spacecraft until Bepi-Colombo provides better data. The high-resolution imaging of the poles will be essential for understanding how the ice is distributed and what surface conditions exist in these regions. Mercury's relationship to the Sun is unique and extreme in ways that shape everything about the planet. The planet exists in a regime of space that no other solar system planet experiences, where solar radiation is intense beyond anything Earth experiences, where the planet is small and unable to retain an atmosphere, where the solar wind is fresh and vigorous, where the Sun's magnetic field is strong, but weakening with distance. This unique position makes Mercury a natural laboratory for studying planetary processes at their extremes, for understanding how planets behave when pushed to the boundaries of what is possible. Mercury represents the outer boundary of where terrestrial planets can exist while remaining intact and differentiated into core, mantle, and crust. It sits at the threshold of what planetary scientists call the habitability zone, though not in the sense of life-bearing pot, Enchel, but in the sense of planetary formation and survival. Beyond a certain distance toward the Sun, closer than Mercury orbits, a terrestrial planet cannot form because the heat from the Sun prevents rocky bodies from accumulating into planetary masses. The violence of the solar wind and radiation environment becomes too intense. But Mercury formed and survived. This fact tells us something profound about planetary formation and planetary evolution. It tells us that rocky worlds can form even under extreme conditions of radiation and solar wind bombardment. It tells us that planetary systems can be robust, capable of existing in regimes we might not initially expect to support planetary bodies. The study of Mercury contributes fundamentally to understanding exoplanetary systems discovered around distant stars in recent decades. Astronomers using advanced telescopic techniques have discovered planets orbiting distant stars in numbers that rival the planets in our own solar system. Many of those planets are in orbits closer to their stars than Mercury is to the Sun. They are hotter than Mercury could possibly be. Yet they exist and persist. Understanding how Mercury survives and functions in its extreme environment provides crucial insights into how those exoplanets might function, how they might maintain their interiors, how they might generate magnetic fields, what their surfaces might look like. The mechanisms we observe on Mercury might operate on exoplanets in similar or analogous ways. The physics of a planet close to its star is the same on Mercury as it would be on a similar planet orbiting a distant star. Mercury serves as a natural experiment, a real example of a planet pushed to extremes, a testbed for theories about planetary behavior at the limits. Mercury is not just a world in our solar system. It is a reference point for understanding planetary possibilities elsewhere, a benchmark against which we can measure exoplanet properties and predict how they might function and evolve. Future exploration of Mercury remains uncertain and dependent on future funding decisions and political will. No sample return mission is planned currently. No lander is scheduled. The closest we come to direct investigation remains orbital spacecraft with remote sensing instruments. Bepi Colombo will provide the best data we have for years to come, will address questions raised by MESSENGER, will likely raise new questions that future missions will need to answer. Eventually, as the decades progress, new spacecraft will be sent to Mercury. Different instruments will be developed, smaller and more capable, more efficient and more targeted. New questions will be asked as understanding deepens and the focus of research shifts to different mysteries. The mystery of Mercury will persist, will evolve, will transform as knowledge accumulates. But the mystery will be different from what it was before each new mission arrives. As information accumulates, the unknown becomes more specific. The questions become more focused and more sophisticated. The mysteries that remain are the deep ones, the ones that might not have simple answers, the ones that might require entirely new ways of thinking about planetary processes and planetary formation to answer fully. Mercury will continue to teach us about worlds at the extremes, will continue to challenge our understanding, will continue to pose questions that drive future exploration and future science.